we've talked about and why it's important. Okay, so here's, if anybody doesn't have, does everybody have the handout that's got the example on it? If you don't, grab one. If you don't have one, okay, so we've got our summary. Remember on this one, this is kind of the first of several process-driven, large topics we're going to cover. So this is related rates that's a big one. Related rates is, that's one of the heavy hitters in first year calculus. Optimization will be another one we'll come up to, like within a month we'll be doing another kind of multi-step process. But it's really useful on this, and what I'm looking for on the, on that paper-intensive test, what I want to see is just that everything's broken down by these steps, that it's organized, right? When we go through the example today, my goal is I want to end up with one page, I'll kind of cut and paste and create this as we go, as we do the work, but have one page that models what it should look like. If you do, when you go through one of these problems and you write out your solution to this, this is kind of what I'd be looking for. What I think is a great way when you go into college, if you just follow this format, this is what, no one's going to complain about that. This is what professors would like to see, right? So remember, real quick review, it's been a weekend here. We got remember that when we're solving related rates problems, this is a dynamic situation. We're always thinking about this in terms of, calculus takes like a static picture and it turns it into a movie, right? So we're thinking about this as a system that's evolving with time, system that's evolving with time, and we're thinking of it as a video. So we've got this, like our example we went through the first day was the balloon was expanding as we blew air into it. Well, that's a pretty simple video. The balloon is just getting bigger as air is added to it, right? But what we want to do with calculus, our goal is to be able to relate the rates of change in the system. Rates of change are calculus things though, right? Rates of change are derivatives, and that's what we've been studying. So that's our goal, is to come up with some mathematical relationship between these rates of change. This is the process we follow. We're going to start off with identify the snapshot values, and we call them snapshots because remember, it's the one frame in the movie. Right? We're going to isolate that one frame, and we're going to write down all of the quantities that are given to us, static and rates, and we'll look at an example in a second, and what it is we're trying to find. We're going to come up with the kind of the pre-calculus relationship between these quantities, which would be, in the case that we looked at on your example, it was volume of a sphere. And then it's not until we get to step 3 that we really do the calculus. Step 3 is where we're going to implicitly differentiate with respect to the independent variable, which is going to be what for physical problems like this? T, yeah. Whether it's a physical problem or it could be an economics problem. We're interested in the mathematical sciences and their applications. We're interested in looking at the evolution of a system with time, right? And so we're going to implicitly differentiate with respect to time, and then that's what introduces the rates. And then the last step is, what is it we're trying to solve for? Well, we'll just isolate that algebraically and plug and chug, right? So let's go through that. Here's our example. So let's kind of just build this together. So we've got this. You're going to see one like this on the third assignment. The sand and gravel plant. Sand is falling off a conveyor onto a conical pile at a rate of 10 cubic feet per minute. So right away, when we identify our static values, our snapshot values, what is that? Okay, it's going to be a V dot, and why is it V dot? So V dot meaning dV/dt, right? What gives it away as being V dot? Okay, so look at, we got cubic feet, which is telling us there's the volume, but then the per minute, right, is telling us that we're looking at the change with time. So that's telling us that we've got rates of change. We're comparing the quantity of volume to the quantity of time. So that gives it away as being a rate of change. So we could add, without even drawing the picture at this point, we could add to our step 1, which is right here, right? We could add V dot equals, and what was that number? 10, right? As long as we're careful and we use the same units, I wouldn't clutter it up with even writing the units down, right? We know that in our case up here, based on just this first rate, what are we measuring lengths in? feet, and we're measuring time in minutes. And as long as we're consistent, we just know at the end, whatever our answer ends up being, we need to use those units to express that answer, right? So we got 10 cubic feet per minute, that's our V dot. They tell us some information here. The diameter of the base of the cone is approximately 3 times the altitude, so that's going to be important to us when we're making our drawing, and maybe in some other ways too. At what rate is the height of the pile changing? So there's our question. What is it that we're looking for? So whatever we're going to call the height, and that's, we're going to call the height, you could call it h, that'd be fine. We could call h for height and r for radius, and that would be fine. The picture that, we're kind of stuck with what I drew, and I called it x and y. Okay, I prefer to just use x and y just because they're variables we're familiar with, but it doesn't matter. It worked the same if you called it r and h. So in terms of the picture that I've drawn, what would that be? We want to know how fast is the altitude, or is the height changing, so y dot. Okay, we're looking for a rate of change of height, right? So then we'll go down to our step 1, and we're trying to find h dot, right? What else is it? You know what I'm going to do just so I can make this skinnier later on. There's our question. Anything else given to us up here? Height is changing when, okay, when h, or in our case y, is 15. Okay? So there are our snapshot values. Okay? All right, so next step would be to create a parent equation. So what do we got here? This is a cross section, but what is this? What shape is this? Cone, right? And more specifically, a right, we call this a right cone. But it's a cone, right? It's just going to look like there's the apex, and then we've got this circular base. Do you remember what the relationship is between, or what is the volume formula for a right circular cone? Well, actually, you see right there. There you go. Right. So 1/3 pi r squared h. Now, there's something that might help you remember. This is kind of interesting. What's the area of a right cylinder, right circular cylinder? So if this were not a cone, but a cylinder of height y and radius x, what would the height be? Or what would the volume? Pi r squared h. And that's easy to remember because it would be like taking like the lid of a can, which would have an area of pi r squared, and we're going to extrude it through space. We're going to move it upward by a distance of h to carve out the volume, right? So we just multiply the area of the base times the height. Well, notice here we've got this 1/3 out front. That's pretty interesting. So what's this tell us about the ratio between the volume of a right circular cone and the volume of a right circular cylinder? It's always going to be 1/3 as big, right? So imagine if we were to somehow cut this right circular cylinder into a cone, and then what would be left? Kind of like it's kind of like a cereal bowl that would have flat sides that would slope down to a point at the bottom. Kind of like you're taking a divot out of this thing. If I separated those two, the top half of that would represent 2/3 of the total volume. The cone represents 1/3. Why the discrepancy? You might think they should be even. Anybody just kind of reason through, unrelated, just interesting, why this has less volume than the divot that's left in the cylinder. It might seem at first blush like they ought to be the same. Why is it? I bring this up because you get in physics, you're talking about angular physics, right? Like rotational physics. Mm-hmm. If you wanted to have a larger moment of inertia for you physics types, where do you want to concentrate? Good luck. Where do you want to concentrate the mass? Do you want to concentrate it more close to the center or further from the center? Okay, further from the center, right? So the further you get from the center, if I were to revolve these points around to carve out area or carve out volume, the further they are from the axis of revolution, the bigger the hula hoops are going to be and the more volume they're going to carve out, right? That's related to this idea of moment of inertia, and we'll kind of draw those later on. We'll kind of come back and revisit that, and you can draw a pretty interesting connection between them. But just a little side. We don't need to get too sidetracked by that. So we've got this parent equation, and in terms of x's and y's, it looks like this, right? We know that volume equals 1/3 pi. Why don't I just put the pi on top? R squared, which was x squared for us, wasn't it? X squared y. Okay? So how many independent variables are there in that equation? X's and y's. So if I really wanted to, I could use this notation and call it v of x and y, right? So do you see potentially a problem with that? So if we're going to start with volume equals pi thirds x squared y, when we get down to step 3, where we want to interject the calculus into this, right? So we're going to differentiate with respect to t so we can get rates coming out. What's going to happen? Yeah, I've got a product rule there, don't I? Right? So when I do the calculus, and we don't need to go through, if we had more time, we could do the whole problem this way, but I want to go far enough that you can see that maybe this is a wrong term for us, right? So if I implicitly differentiate with respect to t, what do I get from the first term? V dot. And then what about over here? Let's just leave the pi thirds out front. And then this is a product, right? So what am I going to get? So I've got, think of it this way. When we use our product rule, we could just group, there's our u, and there's our v, right? So what's that going to look like then? I'm going to get derivative of u, or u times the derivative of v plus v times the derivative of u, right? So u times the derivative of v, what's the derivative of v? Of y dot, because remember, we're differentiating with respect to t. So we've got a y dot plus a v times du. Now I got to use chain rule here. What am I going to get? Everybody see that? Right? Because I've got 2 layers, don't I? I've got the derivative of hand squared is 2 hand to the 1. So there's my 2x. But then if I look inside, the derivative of hand is the derivative of x. That's not 1 because we're differentiating with respect to t. It's an x dot. What seems bad about that?
The x dot.
And for that matter, the x too, right? If we compare this to our snapshot values, the previous page, we don't have very many, right? All we've got is, I guess I should probably go up and change this to, that should be a white option. Right, based on our picture. All I'm given is y dot and y. I don't have x and x dot. Now, could I go back and find those? Yeah, I probably could go back and fill in more blanks up there, but that's some extra work, right? Do you see that there's a motivation for us here to try to get this parent equation written in terms of a single variable? It makes the calculus a lot easier and there's less substitution, right? So is there a relationship up here then in our original problem? Is there a relationship here that we can exploit, what we might call a secondary equation, that's going to relate the 2 variables, we want to eliminate one in favor of the other?
X equals 2/3 y.
Okay, so if we look like right here, how about? They tell us that the diameter of the base of the cone is approximately 3 times the altitude. That's important, right? What's that tell us? That statement says the diameter of the base. What is that in terms of x's and y's? 2x, right? There's my diameter, 2x. So that's saying 2x, what is the word, if we dissect this sentence mathematically, is means what? Equals, good. 3 times the altitude. 3y. There you go. Right, so there's the relationship we need. Now we want to rewrite our parent equation in terms of the stuff that we have, which is a y, and eventually a y prime. So which variable do we want to eliminate? We want to eliminate x, good. So then you gotta think strategically here. If I want to eliminate x, which variable do I want to actually solve for? If I solve for y, let's think about that. If I solve for y, I divide both sides by 3, I'm going to get 2/3 x. That would mean if I plug, that's the variable I want to substitute then, right? So if I plug y into my function here, I'm going to replace the y's with x's. Would you like to change your answer? Because we want to we want to be able to, we want to preserve the y's and get rid of the x's. And so this is a little bit, this is kind of backwards thinking. It's oftentimes the opposite of what you think you would do. But in math, when we want to make a substitution, we want to eliminate a variable, we always want to solve for the variable we're trying to eliminate, right? We want to write the variable that we want to get rid of, which is x, in terms of the variable that we want to replace it with, right? So what's that going to give you? X equals 3/2 y. Okay, and we'll put a box around it because that's our substitution equation. And then we'll just plug that in right there, right? So we're plugging in y equals 3/2? Yeah. Oops. No, x equals 5/6. I told you something. I did the opposite. So we want to write that backwards. I'll make sure my notes are good for you. So we want to make this replacement double. We want to plug in, we want to substitute for x because it's the y's that we have. Okay, make sense? So if we make that substitution, we're going to get v equals pi thirds. And every place I have an x, I'm going to replace it with a 2/3 y. So what do I do with that squared? Yeah, it's got to be the whole quantity that's being squared. And what I'm replacing is just 3/2 y. That's the quantity that's being squared times y. Now we can clean that up a little bit, but already we can see that's much to our advantage. Now we can write this as v of y. Notice in our instructions up here, it always tells us that, right here, let me underline this, whenever possible, the parent equation should end up as a function of a single independent variable, right? That's always going to make our lives easier, right? Turns out the next big topic that we deal with, optimization, it's not only a good idea, it's absolutely essential. We have to be able to write in terms of a single variable. So this is a notion we'll come back to, this idea of introducing a secondary equation that we can use to eliminate a variable. That's a big deal in calculus. It's a very, very useful idea, okay? So if we clean this up a little bit, where do we end up? If I square this out, what do I end up with when all the dust settles here? What's the green stuff going to become when I square it? What am I going to get? The properties of exponents. What's that going to give me? Ryan, what am I going to get if I square this whole thing out? So what's...
9 over...
You're right. 9 over 4y squared. Good. And think back why that is. We know that if we're properties of exponents, if we're taking a quotient and or a product to a power, we're just going to distribute the exponent to all the factors, right? Okay, and then that's going to be multiplied by our other y there. And so now, when all the dust settles, what do we get? We can do a little simplification. 9 over 3 goes to 3, good. And so on the top, I'm just going to get a 3 pi. On the bottom, I get a 4. And y squared times y is y cubed. Okay, so we could agree then that this idea here probably was a wrong turn, right? Because we had too many variables in there. We want to eliminate the variables first, right? So let's instead, let's go on and take a right turn. And I'm gonna, just give me a second, I want to make sure I get all the stuff. So here were our snapshots. Okay, so there's our snapshot values. Parent equation we came up with was this guy, right? So 3/4 pi y cubed, I'll remember that. Was it again, 3/4 pi y cubed. So there's my parent equation. And so now let's try this, let's try to introduce the calculus again. This time it's going to be better though. When we implicitly differentiate this time, it works out much more nicely. And what do we get when I implicitly differentiate? Derivative of the first term is v dot. And then over here, we've only got one variable, so I've got the 3/4 pi out front. What's the derivative of hand cubed? 3 hand squared, so that's going to give us, what, 9/4 pi, hand is y squared, times, what do I have to tack on the end, Lily? Y dot, there you go. Okay, so there's our, done with the calculus. That's the easiest part of the whole thing. Well, a lot of times with these kinds of, these big procedural things in calculus, the calculus is simple. It's the setup and the constructing the problem that takes all the time and effort. So finally, what is it that we're trying to find? Y dot. So we're just going to isolate y dot algebraically, and then we plug and chug, right? Okay, so what does that leave us with? To get the y dot by itself, we can just do this in our head.
Hey, Mr. White, isn't that, do you make that at 9/4?
Did I mess that up?
Also 9/4 is just the 3.
So that was,
Isn't that supposed to be at 3/4?
well, that step, did I, maybe, yeah, I might have messed it up.
You
Let's go.
cubed it. No, you didn't cube it originally, but
Yeah, you cancel out the 3/4.
Oh, yeah, so it should be, it should be 3/4.
9/4 not the last.
Did I write 9/4 here?
that's the-
Oh, I did.
that's
Oh, no, but that's the derivative.
Three.
That's the derivative.
Yeah, see, here's the 3/4. When we differentiate, we bring the 3 out front. 3 times 3/4 is 9/4.
Got it.
Okay? All right, so then, you help me out with this. You guys can, you're great at algebra. You do this for me. So I'm gonna, to get the y dot by itself, I'm gonna multiply each side by what? To isolate the y dot?
1 over whatever it's called.
Okay, sure, 1 over that, but I got a fraction here, so let's break this down into dividing by some stuff and multiplying by some stuff.
V dot times 45.
I got a 4 on the bottom. How do I get rid of that? Let me be more specific. So I'm going to multiply by 4, so I'm going to get a 4 on top. I'm going to divide by everything in the numerator, so I divide by all that stuff, right? And then I've already got a v dot on that side. So we could write this as 4 v dot over 9 pi y squared. Plug and chug, right? So what's that going to give us when we plug in the values? What was our v dot? 10? Positive 10? 9 times pi. Y was 15 squared, and let's see, what's that going to give us? So 40 over 225 times 9. Yikes, what's that going to be? So what was it again?
2025.
That sounds right. 2025 pi. And then we could divide everything by 5. So that's an 8, and that's going to be a 405 pi. So our final answer then just looks like y dot equals what about units? What would the units be? Based on the context of our problem, y dots, we're measuring the rate of change of height. So it'd be feet per minute, right? We need units of height, which are feet, divided by units of time, which are minutes. Good, so we end up with feet per minute. There it is. One problem. Okay. The main issue though, what separated this from the other ones? Just the fact that we had to combine, we had to use that secondary equation to rewrite the parent equation in terms of one variable instead of two. That saves you, I mean, you can see how much time that would save us. If we were just to look back here at our horrible wrong turn, the horrible wrong turn, we would have had to fill in a lot of stuff, go back and geometrically fill in a lot of steps in that snapshot values, right? We could have done it, but much harder, definitely far preferable to simplify the parent function first, write the parent function in terms of a single variable, then everything from that point gets a lot easier, right? And you're used to that in calculus lots of times. Investing a little time up front to simplify before you do the calculus, as we've seen, is well worth it, right? So, all right, go. Get your questions answered. I'll make sure this gets updated today so the videos and notes are all good to go.
I'm going to the bathroom.